Your warm-up is in My Open Math, and we're going to go over it. If you haven't answered it, you can fill it in after we go over it. And then we're going to get into today's notes. We're going to be talking about projectiles that are launched at an angle. So we'll have some notes going over just the concepts related to that, some graphs, and then we'll get into a math example calculation. But you will have more of those in your homework assignment, 702.3 Mixed Projectile Motion Problem Set. I'm going to strongly encourage you to start that assignment today. It is not due today, though. It is due on Tuesday of next week. As a reminder, you do not have school on Monday. So that will be due on Tuesday. So let's go back to the warm-up question. It says, a plane at constant velocity drops a relief package. Where does it land? And you're looking at this image on my screen. First of all, there is no air resistance. I typed that up here. We're going to assume that somehow this plane can fly without air resistance. Just go with me here. And we have this plane carrying a package, and this guy's going to drop the package right here, and then it's asking, when the plane is at this position, where would the package be? A, B, or C? And so what you need to keep in mind as you answer a question like this is that your plane and your package are initially moving together. Okay, so let's say they're both moving 200 kilometers per hour, then they're both moving that distance horizontally, each hour. Okay, and so if you look at it, the box is also moving at that speed. When he drops the box, it becomes a projectile. And if there's no air resistance, which it says there isn't, then the only force acting on the box after he releases it is gravity, which means there would be nothing present to cause the box's horizontal velocity change. There is no horizontal force. This is very similar to the Mario banana peel question the other day, because we would expect them to keep pace with one another, and therefore it would land directly below the plane at point B. And again, if we draw that in, that's because each second they're moving the same distance, and the box is doing the same thing. It just happens to also be falling. But because there's nothing horizontally, no force is acting on it, it should maintain that same speed. Now, the reason this seems so weird to us is that we know if we actually did this in the real world, it wouldn't land there. And that's true because there is air resistance in the real world. And so, of course, it's not going to be directly below it if you were to go outside and try dropping something out of your car while you drove past. It's not going to do the exact same thing because of the presence of that other force. But if we remove that and if we analyze it as this ideal scenario for this projectile motion, it should do that in the absence of air. Okay, so that's how we're going to answer it, is what it should do when there's no air resistance, and it should land directly below it at point B. Please make sure that you have answered that question in your warm-up so that you're getting credit for it. Are there any questions about this? Okay. Here's an animation, by the way, showing the same thing. You can see that even though this object is falling, its horizontal position, the points, are all keeping in line with the position of the plane. And so their horizontal motions are the same. It's just the vertical that's different because the plane doesn't have vertical motion, whereas the package is, of course, falling. All right, so we're going to try this example problem going all the way back to Unit 2. Before we start talking about projectiles that have been launched at an angle, which means that they have been launched with both an initial horizontal and vertical velocity, we're first going to talk about some free fall stuff that we did in Unit 2. We talked about objects that were thrown straight up in the air, okay, like this one. In fact, this is a slide from Unit 2. And so whenever we talked about it, we talked about some different tips and just things you need to remember about the nature of free fall motion that are going to apply to the scenarios that we're about to do today. So we need to really remember all the way back to free fall. It's going to help us whenever we start adding this motion in with our projectiles, because you're going to have this up and down. It's just it's also going to be moving forward. Okay, so we'll start here with free fall. We'll go through a couple of free fall examples, and then we'll get into our projectiles that are launched at an angle. If you want to copy this down, I would recommend that you do it so you have it to look back at. It says a ball is thrown upward at 3.4 meters per second from the ground. What will be the maximum height that it reaches? And you're going to have questions that look kind of similar to this. Of course, we're going to have a little bit different information, but kind of similar to this when we deal with our projectiles. So we need to analyze them in a similar way. So we're going to start by labeling what we know. Now, I'm not going to make a table for my horizontal and vertical data because this particular object is just going straight up. So I don't have any horizontal data to account for. I would just be filling it in with zeros. Now, if you want to make a table, you can, but I'm just going to, I already know these are all vertical. So here's my initial vertical velocity. It's positive 3.4 meters per second, or 3.4 meters per second straight up. Okay, and that's the only number in the question. So because it appears that there's not enough information given to us, we need to start thinking about what else do I know to be true about a projectile thrown straight upward. What's the first thing that comes to mind? What else do I know is true about something if it's thrown upward, or if it's in free fall? Acceleration is what? Negative 9.8 meters per second squared. I know that. Okay, it's not going to be told to me in the question, but I know that my vertical acceleration, and everything here is vertical, so it's just my acceleration, is negative 9.8 meters per second squared. Okay, I know that because it's in free fall, and that's going to be true for our projectiles as well. Okay, now it's not given to me, but I know that. So that's, again, I still need to ask myself, what else do I know that could help me? What else do I know about this projectile? Anybody remember from last semester? I know I'm asking you to think back several months. Sorry?
Final velocity is 0.
Okay, final velocity is 0 if we're talking about this point at the top. Okay, and so I can write that as VF and call my final point that point. You can call whatever point you want your final point. You can solve for it to any point. Or you can write V top if you prefer, or V max, or whatever, although that would be kind of confusing. Max height, I guess. But here is my final velocity at the top is 0. I also know that to be true. And that's super helpful because if I'm trying to find out what the height is at that point, it's helpful for me to know how fast it's going at that point. Again, that number's not given to me, but I know it to be true. I know if I throw something up in the air, it's going to slow down, it's going to stop for just an instant, and then it's going to fall back down and speed up again. Okay, and so I have this piece of information. Even though it's not in the question, I know it to be true, and it's going to be true for our projectiles when they're launched at an angle as well. Their vertical velocity will be 0 at max height. Okay, so I can now use this information to solve for the maximum height. I can find that displacement. It is a vertical displacement. I could have labeled it delta y, but I just left it alone with what we had in there last semester. We were only dealing with one dimension, so I just labeled it as delta x. Okay, so I have my VI, A, and VF. I'm looking for delta x, and these are my kinematic equations. Take a moment to look at them. Which equation could I use to solve this in one step? A, B, C, or D? B. I'm going to use equation B. Now, could I use equation A and find time and then find delta x? Yes, I could. You're more than welcome to do that. Okay, but if I want to solve it in the most efficient way, I'm going to go ahead and just use this equation because it has my variables in it already. VF squared equals VI squared plus 2 times A times delta x. If I substitute in, that is 0 squared equals 3.4 squared plus 2 times negative 9.8 times delta x. 3.4 squared is 11.56. I'm going to subtract that 11.56 so that it gets over here and cancels here, and that's going to leave me with this. Negative 11.56 equals 2 times negative 9.8 is negative 19.6 times delta x. Okay, my next step algebraically to isolate my variable is to divide both sides by negative 19.6. So negative 11.56 divided by negative 19.6 gives me a displacement of positive 0.59 meters. Okay, so that is going to be my displacement at the position where my final velocity is 0, so at the max height. That is my answer. Okay, are there any questions about this example? We did this exact problem in Unit 2. I know you don't remember every problem we did, that's okay. But hopefully you remember the idea behind it. Okay, if not, we're going to be doing some more. So that's your max height. Follow-up question, how long is this ball in the air? What's its air time, its hang time, total air time? Okay, now you'll notice that I have my given information. I recopied it here and I added that displacement that I just found. However, if I use these numbers to find time, which is what I'm about to do, that means I'm only finding the time to get to this final position, to get to this maximum height, which is good. I can use that. Okay, but it's not going to be my final answer because the time that it takes to get to the max height isn't the total time. It's just the time it takes to get up. So we'll talk about what to do with that in a minute. Okay, but I'm going to solve for the time, but it's going to give me just the time to that final position that I chose. Okay, I have VI, A, VF, and delta X. I can find time with any of the equations up here that have time in them, which means I can use A, C, or D. Doesn't matter. Personally, I find A to be the easiest because it's the most simple looking equation, so that's the one I'm going to use. VF equals VI plus A times T. Substituting in, that is 0 equals 3.4 plus negative 9.8 times T. If I subtract 3.4 from both sides, I get this. Negative 3.4 equals negative 9.8 T, and then I'm going to divide both sides by negative 9.8. Negative 3.4 divided by negative 9.8 is 0.347 seconds, but again, that is only the time it takes to get up to the top. So what do I need to do to get the total?
Multiply by 2.
Double it. Yeah, multiply by 2. Because time up equals time down. This is another thing we talked about in the free fall unit. The time it takes to get up to the top is equal to the time it takes to get back down. So we have to double it. So when I double it, I get this, 0.694 seconds, and that is my answer. Again, this is the same type of thing you'll be doing when it's also being launched forward, because the vertical motion is going to look the same whether it's thrown straight up or whether it's thrown forward and up. All right. We also need to remember these. You're going to see graphs again. Okay, so let's talk about what our graphs would look like. Okay, our position time graph for this projectile thrown straight up, I know that it starts out moving upward, which means I need to start out with a positive slope, and I know it's going to end moving downward, which means I need to end with a negative slope, but I also need my slope to change because there's acceleration, so I need a curve. It's going to curve and then come back down again. It's going to look like this. It starts out moving faster, moving up. It's going to flatten out at that very top point where it turns around. That moment in between the two, that's where it has stopped. So this would be max height, and then it's going to go down and speed up again. Okay, so that is what vertical position time graph will look like, and it's going to look like that regardless of whether I throw it straight up or throw it forward at an angle. That's what my vertical position time graph will look like. For my velocity time graph, again, I'm starting out with an object that's moving upward, let's say with 20 meter per second velocity, and then 10 meters per second, and then 0, and then negative 10, and then negative 20. I'm going to have a uniform change in velocity. The rate of change in velocity is going to be constant. Specifically, it's going to be negative 9.8 meters per second that it changes every second, right? That's acceleration due to gravity. So because I have this constant change in velocity, this constant rate of change, I do need a straight line. It's going to have a slope to it. It's going to start out up here moving in the positive direction. It's going to end up down here moving in the negative direction. It has to cross the x-axis because when it touches the x-axis, it's moving exactly 0, which happens up here at the top. And so it's going to look like this. Okay, you're going to have a straight line with a negative slope that crosses your x-axis. Okay, and that negative slope, again, represents the acceleration. The slope of a VT graph is your acceleration, so the slope of that would be negative 9.8 if I had numbers there. When I get over to my acceleration graph, again, I have a constant rate of acceleration. Yes, it changes direction. Yes, my velocity goes from positive to negative, but my acceleration is negative 9.8 meters per second squared the entire time. Okay, it's what causes it to slow down as it rises. It's what causes it to speed up as it falls. So this is your AT graph. So again, this is what your graphs look like for any object in free fall that has an initial upward velocity. And that's true if you throw it straight up, but it's also true if you throw it up at an angle. That's the vertical. Okay, so just a quick recap, because I know we haven't looked at these graphs in a little bit. All right, one more thing we're going to look at for our object thrown straight upward, and then we're going to get to talking about something that also is moving forward. Okay, so this one says a ball is thrown straight up from the ground. Labeled positions are shown at each second. Identify the direction of the acceleration and velocity at each point. Okay, I know that my velocities start out positive and end up negative. I know that. It starts out going up, slows down, stops, and then is going down after that. So I know that points A, B, C, D, and E are all positive velocity. I know that points G, H, I, J, and K are all negative velocity, and I know that at the very top at point F, my velocity is 0. So I have positive velocities A through E, negative velocities G through K, and 0 velocity at the top. But although my velocity changes, my acceleration doesn't. Again, don't mix the two up. Okay, my acceleration is a constant negative 9.8 meters per second squared, and therefore it's always negative. So the direction of my acceleration is down the whole time. The second question says, where is the ball moving fastest? And it's going to be moving fastest the moment after it's launched at point A and the moment before it lands at point K. And that's because at point A, just after it's launched, now it's going to start to slow down. It's going to get slower and slower and slower. So the fastest it's going is right here. And then it's going to fall back down and it's going to speed up. And because these are at the same height, they're going to be moving the same speed. They're just going in opposite directions. Okay, so A and K, or A or K. How does the speed of the ball compare at D and H? And again, I just mentioned this. If the points are at the same height, you will have the same speed. Different direction to it, but same speed. So I would say that they are equal. Again, all of these things that we just used here, we're going to apply in a second to our projectile that has an upward component to its motion. Okay, so what if it's launched at an angle? What if it's not just straight up? Okay, this means that we have initial velocity in both the horizontal and vertical directions. And you can see that here. I've drawn in some velocity vectors. This object has a constant velocity moving forward, represented by these red vectors. They're all the same length. But vertically, we see the exact same type of thing we saw with the object thrown straight up. It starts out moving faster, it slows down. Up here at the top, it doesn't have any vertical velocity at all, and then it starts to speed up and gets faster as it falls. Okay, so now we have these two things working together to give us this curved path. Again, we still keep them separate, just like we did with all of our other projectile motion stuff, because we still have horizontal constant velocity and vertical acceleration. So we have to keep them separate. We're going to use the same types of tables in our calculations. But before we get to the calculations, though, let's go back to the graphs. I mentioned this a moment ago. But the vertical motion of this projectile is going to look just like the vertical motion of the object thrown straight up. Okay, its position, initially you're going to start out with a positive velocity that starts out fast, slows down, and stops. That's going to look like this. Starts out with a steep slope, gets less steep, stops. And then it's going to turn around, and it's going to be a negative slope, and it's going to get steeper. Same shape that we just looked at. My velocities are going to start out positive, positive 20, positive 10, 0, negative 10, negative 20. They're going to cross this axis right here at max height, and it's going to turn around and go the other way. That's what my VT graph looks like. I do have a constant rate of change in velocity. It's a straight line. And that rate of change in velocity is negative 9.8 meters per second squared. It's a constant acceleration. Okay, so that's exactly what our graphs looked like for our projectile thrown straight up. Okay, so vertical motion is the same, whether we throw it straight up or up and at an angle. However, because this one is also moving forward, we can also draw the graphs for horizontal motion. The other one I didn't have any horizontal motion, but this one I do. I've called it 10 meters per second the entire time. If you're moving 10 meters per second the entire time, that means that you're going to have a straight line on your XT graph, because it means after 1 second you'll have gone 10 meters, after 2 seconds 20, after 3 seconds 30, after 4 seconds 40, so on and so forth. You get a line that looks like this. Straight line, positive slope, because it's positive 10. For my VT graph, I have constant velocity. It's not changing. So I need a horizontal line on my VT graph. And again, if there were numbers here, this would be at 10, because it's 10 the whole time. So I just have a horizontal line showing it's not changing. My acceleration is, of course, 0. There's no change in my velocity. We already know this. We've been filling a 0 into that table when we do calculations. So we're going to put it on the x-axis. Again, I know we haven't looked at these graphs in a little while, but this is a review of stuff from last semester. You still need to know how to represent different types of motion in a graph. So we have now constant velocity with our horizontal graphs, and we had acceleration with our vertical graphs. So just a few things you need to remember about these projectiles before we get to the calculations, and I would write these down if I were you. Okay, if your projectile is launched, again, at an angle on level ground, then time up equals time down. Okay, again, the amount of time it takes to rise up to the top is equal to the amount of time it takes to fall back down to the ground again, assuming you're going back to the same height. That's why it says level ground. Okay, the other thing that's also true is if you look at the velocity of this football right after it's kicked, its initial velocity, and if you look at that point right before it lands, you're going to have the same magnitude of velocity. They're the same speed. Opposite directions, but same magnitude. So if this is positive 20, this is negative 20. Okay, so again, those 2 points, if they're at the same height, they're going to have the same magnitude of velocity. And then, of course, this maximum height, this point up here, is at 1/2 the total air time. So if you're solving for max height, or if you're using the max height to solve for something else, make sure you're using half your total air time. We just did all of those things with the free fall stuff, so that's why I said it's all related. It's very similar. All right, let's go ahead and try an example calculation, and if I were you, I would copy this down so that you have it to refer back to. Again, we're going to want a table to keep our data organized so that we can keep our vertical and horizontal data separate. But another good idea would be to sketch out the trajectory. You can see my picture at the top. I have a trajectory sketched out, and the reason this is helpful is because now I can label points on it. I can label my range if I know it. I can label my height. I can, label what I know about the max height or the initial or the final. So it does help to organize all of your information if you sketch out a picture. I know right now there's nothing on it, but we can add stuff to it as we get information. We can start adding it to our picture if we need to. The question says, a soccer ball is kicked 24.5 meters per second at an angle of 35 degrees above the ground. How far away will it land? Again, in this example, we have an object that has a diagonal velocity because it was kicked both forward and upward. And so we have this 24.5 meters per second, but it's at this angle with the ground, this 35-degree angle. So whenever I go to fill in my table, I'm not going to write 24.5 meters per second for my vertical velocity because it's not vertical. I'm not going to write 24.5 meters per second for my horizontal velocity because it's not horizontal. I'm going to have to find the components. The components go into my table. Okay, but before I do that, I'm going to fill in some things that I already know to be true. Okay, I know that my accelerations, are negative 9.8 meters per second squared vertically and 0 meters per second squared horizontally. I can always fill those in. Okay, and that's actually the only thing I know right now, other than that velocity that's at an angle. Okay, so the next thing I'm going to do, and if you have a velocity at an angle, you can actually start here if you want. The first thing you should do, or after you've labeled your accelerations, the next thing you should do is to find the components, which means you have to use trigonometry, SOHCAHTOA. Okay, so if I want to solve for those, I can solve for this initial vertical velocity using sine because it's opposite my angle and I know the hypotenuse. It's the SO and SOHCAHTOA. The sine of 35 degrees equals opposite over hypotenuse. If I want to solve for this VI in the y direction, I'm going to multiply both sides by 24.5, and that's what goes in my calculator, 24.5 times sine of 35 degrees. Again, if you're typing this in the calculator, please make sure you're in degree mode. If you're not, you're going to get it wrong. Okay, but when I multiply that and I'm in degree mode, I get 14.05 meters per second. So that's one of my components. That's my vertical component. I'm going to do the same thing to find the horizontal, but my horizontal component right here, this pink one, it's adjacent to my angle. I have a hypotenuse and an adjacent side. I'm going to use ca, or cosine, the ca of SOHCAHTOA. Cosine of 35 degrees equals my adjacent side, VIX, over 24.5. Again, we're going to multiply both sides by 24.5. That cancels, and in my calculator, if I type 24.5 times cosine of 35, I get 20.07. You'll notice that I filled it in for both the initial and final because horizontally it doesn't change. It's the same number the whole time. All right, so that's the information that I have from the question and from what I know about the object's acceleration. But I ultimately need to solve for how far away this thing is going to land. Yes. All right, so if we want to solve for how far away it will land, we obviously are looking ultimately for this horizontal displacement. But in order for us to find that, we have to have time. And I told you this the other day, but one of the first steps you're going to do, now here our first step is get components, but after that it's almost always going to be find the time. And so we're going to be looking for the time in order for us to finish solving this problem. Okay, so if I want to find time, I'm going to have to use the vertical data. I can't use the horizontal because I don't know the displacement. In fact, I need the time to find the displacement. But I also don't currently have enough information about the vertical motion of this projectile either. Okay, so I need more information. What else do I know about my projectile that I could use to find time? I know the final velocity. Okay, remember, it's not labeled in here right now, but I know what it is. Now, it depends on what point I choose. I could pick the maximum height, and I could say the final velocity here is 0, and I could solve for the time, but that would only be half the time, and then I could double it. Or I could pick this point at the end, because if the initial velocity here vertically is 14.05, what's my final vertical velocity at the end? Negative 14.05. That's what I'm going to do. Now, you could do it either way, but I'm going to actually use the final point at the very end. When I do that, I also happen to know my displacement because I started and ended at the same height. My displacement is going to be 0 if I choose the very end. Okay, and so I have filled everything into the vertical, and if you want, you could write above this on your table like vertical at impact or something like that, so you know you're going all the way to the end and not to the midpoint, because sometimes you will use the midpoint, and if you do, you might want to label it. So I've got all of this. I can find the time now because now I have VI, VF, A, and delta X. So I can use any of these equations to find time. Okay, I'm going to go ahead and use the first one because it's the easiest. VF equals VI plus A times T. So that's going to be negative 14.05 equals 14.05 plus negative 9.8 times T. Again, you can only use numbers from the vertical side of the table. Don't pick from both sides. Okay, that's going to become negative 28.1 equals negative 9.8 T, and then I'm going to divide by 9.8. I don't have all the math written out here, but you can work it out on your paper. Okay, I showed you which equation I used, and here's my answer. 2.868 seconds. So that's my total air time from launch to the point where it's landing, where it has that negative 14.05 meter per second vertical velocity. So I just found my time. And now that I have my time, I know I can use that on my horizontal side as well. Now I can find my range. Okay, and if I want to find my range, I have to use just the horizontal data. I have VI, I have VF, I have T. I'm looking for delta x. The only equations we can use for this horizontal are going to be B or D, and it's because they end up being the same thing. Both of them say displacement equals velocity times time, because if I use this equation and I put a 0 in here for A, because the acceleration is 0, this whole term goes away. And it's displacement equals velocity times time. This one also says displacement equals velocity times time. It's the same thing, pick one. Okay, the bottom one's average velocity times time, but it's the same the whole time, so the average is the same. Okay, so if I substitute in, that becomes velocity 20.07 times time 2.868, and when I multiply those numbers, I get 57.56 meters. Again, I didn't show all the work. Okay, I didn't have enough space up here, but you can write it out on your paper. You know which equation I used, or you could use D. Okay, and you should get that answer, 57.56 meters. Questions about that one? All right, let's look at another one, or actually a follow-up question. Okay, so my soccer ball, same scenario, but now I want to know what is its maximum height. Guys, if you have to solve for maximum height, you need to look at the vertical data for the maximum height. Okay, I'm going to add another column to my table. Okay, and I'm going to label it. I'm going to write at impact over here because this was for the end point, the very end. And over here, I'm going to write max height because now I'm looking at just to the max height. Okay, if I'm looking at just to the max height, my initial velocity is still the same as it was here. It's still 14.05. My acceleration is obviously the same. It's still gravity. Okay, but what do I know about this max height? What is my final velocity up here? 0. I'm not going to use the negative 14.05. I'm going to use 0. My final velocity up there is 0. What about my time? What do I do to find that? It's half. It's not going to be 2.868. It's going to be half of that because it's only halfway. Okay, and so half of that is 1.434. Make sure you do this whenever you're trying to find max height. Use half the time and a final velocity of 0. Okay, and so now I can solve for that displacement vertically using the information in this column and only in this column. Don't mix, okay, just that column. And so if I want to find that max height, I'm going to go ahead and use this equation. It's the third one on my board. On my board it says delta x equals VIT plus 1/2 AT squared. I went ahead and labeled it as delta y because technically it's my vertical displacement. And so I have delta y equals my initial velocity, 14.05, times my time, at least half of my time because I'm just looking to go halfway. Okay, and then plus 1/2 times negative 9.8 times 1.434 squared. If you plug all this in your calculator, you should get this, 10.1 meters. Guys, please be careful with your signs. If you don't type negative 9.8, you won't get that answer. Okay, so make sure that you type that negative sign in there so that you end up subtracting rather than adding. Okay, but it should be 10.1 meters for the maximum height. Questions about this? All right. Then for the rest of the class period today, you should be working on the assignment 702.3 Mixed Projectile Motion Problem Set. This is not due tonight, it's due Tuesday. Okay, but I would very strongly encourage you to get as much of it done as you can. In fact, I would try to have half of it done before you come to class on Tuesday so that you're not trying to do the whole thing on Tuesday. Some of these problems can take a while, especially when you're not familiar with it yet, so they'll probably take you longer, and as you get better at it, they'll go faster. But I would try to get as much of it done as you can. Aim for half. That way you only have half of it left whenever you come into class on Tuesday. We'll do some more notes. Obviously, if you're not sure about them, you can skip those and maybe try a different one. And obviously, if you have questions, please ask them today before you leave so that you feel comfortable with it, or as comfortable as you can anyway, whenever you go home for the weekend and maybe work on some of this. As a heads up, next week we will be working on an RA where we are going to be building a catapult. The catapults are going to be kind of small like this. They're built out of popsicle sticks, rubber bands, and spoons. So you might want to start figuring out who you want to work with, so you can start figuring out what supplies you want to bring in. This particular group used hot glue to put theirs together. That is an option if you want to bring it in. Okay, but popsicle sticks, rubber bands, and a spoon would be your bare minimum in terms of materials. So you can work in groups of 2 to 4 on that project for the RA. We'll be talking about it next week, obviously. But if you want to start talking about it now, you can. And then again, what I would focus on primarily today is the assignment 702.3. If you have questions as you're working, please let me know.